and we're going to discuss the JP Morgan's Quorum in the following slides.
Okay, so what is Quorum? Quorum is a lightweight fork of Go Ethereum. Its design has been created to be simple, so any future changes in Go Ethereum can be easily maintained on Quorum. Quorum is like Ethereum but with different consensus algorithms, access control, and the ability to say that this transaction is private only for those people. In other words, other people can see what's inside. So the actual content of the transaction is transmitted only to those people, and what goes in the blockchain is the hash digest.
Quorum is providing permissioned implementation of Ethereum, which means that only permissioned parties can connect can connect to you and have access to the payload transaction. And this is done using the following: transaction and contract privacy, and the multiple voting mechanisms of consensus, and the network peer permission management, and the higher performance.
This is what we are going to discuss today. We'll first begin with the transaction processing and privacy. Okay, so every transaction has a field called private for, which is an array of all the public keys that will be parties of your private transaction. Also, the transaction has a private method which identifies the private transaction, and this is a screenshot of a normal Quorum transaction, which has the private for and field with the public keys.
Now I will discuss the flow of how the transaction is processed. First of all details of the transaction are embedded into it. That means that those details are then swapped up with the cryptography hash, and that's what is being put into the blocks where they are being shared across the network. I'm gonna say that when a node validates a transaction, it checks if it's party or of this transaction or not. As I mentioned before, that only permitted users can have an access to the transaction. So the transaction manager then checks if the signature matches its identity. If so, it is a party of this transaction and it can have access. Then it responds with a payload, maybe a 256 bit hash, which can then decrypt. The other party can decrypt this hash. Then we have a node that passes into the EVM to execute the smart contract.
As a result of this, each node only validates the public transactions or the private transactions it is party of. Each node only has a partial, each node has a partial state of the blockchain. All the nodes validate that all the transactions are complete in every block by hashing the block and comparing it to the hash in the header. So we know that these transactions haven't been touched. In other words, it has been immutable, and everyone have that same unique blockchain of all the transactions because everyone can derive a state given the enough information. Again, every node validates only the transactions that are either public or private and is a party in it. Because nodes don't have to execute the code of the transactions that they are not party of, this improves considerably the performance of the Quorum.
Thus, in details how a transaction is processed. First of all, party A sends the transaction to their Quorum node, specifying that the transaction payload and setting private for to be the public keys for party A and party B.
And then party A's Quorum node passes the transaction on its transaction manager, requesting it to store actually the transaction payload.
After that, party A transaction manager makes a call to its associated enclave to validate the sender and encrypt the payload.
And then party A, the enclave of party A, checks the private key for party A, and once validated, it performs the transaction conversion, which is just like generating the symmetric key and encrypting it and doing the SHA-3, which is the 512 hash of the encrypted payload, and iterating through the list of transaction recipients, which is in this case party A and party B, and encrypt the symmetric key of each, and with the public key of each party, and then returning the encrypted payload and the hash and the encrypted keys of each recipient to the transaction manager.
Then the transaction manager for party A will store the encrypted payload, which is encrypted with the symmetric key and the symmetric encrypted key using the hash as the index. Then it will securely transfer the hash via the HTTPS encrypted payload and encrypted symmetric key that has encrypted with the party B's public key to the party B's transaction manager, and the party B's transaction manager will respond.
And then the sixth step will be once the data transmission to party B's has been successful, party A's transaction manager returns the hash to the Quorum node, which then replaces the transaction original payload with the hash and changes the transaction V value to 36 or 38. This means that it will be it's a private transaction. If it was a public or anything else, it would be like 20 something value.
In step 7, the transaction is propagated to the rest of the network using the standard Ethereum peer-to-peer protocol, which is simply then go to step 8, which the block containing transaction A and B is created and distributed by each party on the network.
Okay, and then when a party wants to create a new block with the transaction in it, it will set it to its node, and then the transaction manager sees if it's if it is a party in the transaction or not. So for example, here party C is not a party in the transaction AB. So the transaction manager C will respond with a transaction not found because he is not a recipient in the transaction. So party C will not proceed with the transaction processing, but party A and party B will continue the processing of the transaction because they are party of it.
Okay, well, and here the enclave validates the signature, and then it decrypts the symmetric key after we make sure that party C is not a party of the transaction, and we have party A and party B. We will use the party's private key that has held in the enclave, decrypts it in the transaction payload using the now revealed symmetric key, and return the decrypted payload to the transaction manager.
And the transaction manager for parties A and B then sends the decrypted payload to the EVM, Ethereum Virtual Machine, for contract code execution. This execution will update the state of the Quorum node's private state database. So as we have discussed earlier, every node has its own partial state database, which is so every node has a unique state database, and by collecting them all, we will have the complete database.
To the security section, we will talk about the network permissioning, which is a feature that controls which node can connect to a given node, and also to which nodes the given node can dial out of it. Currently, it is managed at individual node level by the permissioning command line flag. When starting the node, if the permission flag is set, the node looks for a file.
This file contains all the nodes that are permitted to connect to and accept connections from you. And this is a sample of the file of the JSON file that contains the eNodes that are whitelisted in your network, and this is a real sample file. So yeah, this is just a placeholder of this.
Now turning to the consensus section, we have two consensus in the JP Morgan quorum. It's a quorum chain and the raft. First of all, I'm going to talk about the quorum chain. It's a time-based vote-driven mechanism, which we will use, which in the nodes have roles like a block makers or voters, and might be observers. Consensus rules can be modified from the block voting smart contract without a hard fork. That leads to the configuration embedded in the Genesis block. And now turning to the raft.
The raft is a well-known consensus algorithm for distributed databases. It relies on a single leader for a term period. So every leader is elected when the term period is over. The leader proposes blocks, and others all what they are doing is just validating, and the leaders are selected randomly. And there are plenty of other algorithms like the Istanbul
Byzantine.
the Istanbul Byzantine algorithm and others, but we are running out of time. So thank you for having your attention. And this was Mazen and Mobs.